Yo, what's up guys? Welcome back. Patrick here, moving on to the next video in stats. We're now going to talk about standard deviation. And standard deviation falls under the section of variability, so we're still in the variability section. And so far what we've covered is a couple of different measures that we can use to describe the variability of a data set. So one measure we talked about was range. Then we spent more time on the next measure, which was quartiles, and then we talked about how we could visually represent those quartiles through a box whisker plot. Well, now we're going to move on to the next measure, which is standard deviation. And actually a measure that's very closely related to standard deviation, which I'm going to be talking about a lot in this video as well, I'm going to keep bringing it up, is variance. They're both really closely related, but the more popular one is standard deviation, but throughout I'll talk about the variance as well so you understand what it is. So standard deviation, the way I like to think about it in words is basically how far the observations in a data set deviate, hence standard deviation. So how far the observations in a data set, how far they deviate or how far they vary from the mean or the average of the data. And there's going to be a technical formula that I'm going to show you how to calculate that, both the standard deviation and the variance. However, we're actually going to split up this calculation of standard deviation in two different sort of groups. One's going to be the population standard deviation and the other is going to be a sample standard deviation. It's a common source of confusion, the difference between the two for students. So I'm going to spend some time talking about the differences. And basically what's happening is, let's say that you have a population that you're looking at of data. So this could be maybe like all the people in a certain city. Okay, so this here is the population. It's basically all of the data points or all of the observations that you are looking at for a certain population. However, in reality, what happens, especially if these populations are really big, is that if you were to examine all the observations or all the data points in a certain population that you're looking at, it would take you a lot of time. It would take a lot of resources. So what we do in stats is we take a sample from the population, we analyze the sample, and then we make a general conclusion about the population. So that's pretty much how stats works. And so what we're going to be talking about is how do we calculate the standard deviation for a whole population? And how do we calculate the standard deviation for a sample? There's a couple of small differences between the two. Now, before we get into that, one thing I want to mention is throughout this video, you're going to see a capital N coming up and then a small n. Now, this capital N, what I'm letting it be is the number of observations or number of data points in the population. Okay, so that's going to be the total number of observations in the population, while small n is going to be the number of observations in the sample. Okay, so when I'm talking about the population standard deviation, you're going to see this capital N come up. When I'm talking about the sample standard deviation, you're going to see this small n come up. And so just from here, you can tell that this small n is always going to be less than the capital N, right? Because a sample is going to be within the population. It's just a smaller group. We're going to analyze a sample and then come up with a general conclusion about the population. Okay, so let's introduce how this standard deviation works technically first. I'm going to introduce the formulas. And then what I'm going to do is I'm going to do an example of where we're taking a population, finding the standard deviation for that population, and then taking a sample from that population and then finding its standard deviation. But let's introduce the formulas first. So again, we're going to split it up here. We're going to have the population, standard deviation, and then we're going to have the sample, standard deviation. Now the population standard deviation is usually represented with the Greek letter sigma. And basically what it is you're taking all of the observations in a population. So let's call them x1, x2, x3. And you keep going all the way to x capital N. Right? So if there's 1,000 observations in the population you're looking at, this would be 1,000 terms here, right? 1, 2, 3, all the way to x 1,000. So what we're going to be doing is we're going to be taking those observations and we're going to be seeing how far they deviate or how far they vary from the mean. Okay, so the mean for a population, it's usually shown as mu. So this is the mean of the population, which is basically just the sum of all of the observations. Sorry, not xn. Let's put an I there. So this is this sigma here represents that we're summing up all of these, and it's going to go from 1 to n. From 1 all the way to n. So we're summing up all of the observations and then we're dividing by capital N. Right? Just the average of all of these. You add them up, divide it by the number of observations. In this case, since we're dealing with the population, it's capital N. So you get that mean, and then what you do is you figure out how much deviation for each observation is happening from the mean. So you're going to take each observation and you're just going to subtract the mean from it, seeing how far each one is away from the mean. And then what you're going to do is you're going to take all of those deviations and you're going to square them. Okay, so without the square, before I wrote this power 2, those were the deviations. After you square them, these are called the squared deviations. And so what we're going to do is we're basically going to add up all of these squared deviations. So I'm going to put another sigma here. And we're going to go from x1 all the way to xn. Right, so I put an I here, so the I is going to start at 1, and then it's going to finish at n. So we're taking all of those square deviations, adding them up. That's what this means here. So this is the sum of these square deviations. And then we're going to divide by n. We're going to average them out. So we're summing up all those square deviations, and then we're going to divide by the number of observations in that population. So we're taking the average of the square deviations. And then once we have that, what we do, because we squared it here, what you want to do is you want to square root that number like that. And that there is your formula for the population standard deviation. And again, I'm going to show you how to use it with an actual data set in an example soon. But this is the formula for the population standard deviation. So you are taking those square deviations, summing all of them up, averaging them out, dividing by n, and then you're square rooting that number. So this here, just want to make a note, it's the population standard deviation. Now I mentioned that the variance is very closely related to standard deviation, and basically the standard deviation is always the square root of the variance. whether you're working with a population or a sample. So the population standard deviation is always the square root of the population variance, or the sample standard deviation is the square root of the sample variance. And another way to write this is we can kind of take this square root, put it on this side, so we would square both sides. So we could say the standard deviation squared equals the variance. Usually textbooks will show the relationship like this, but this is the exact same thing. That's another way to show this. Both of these mean the same thing. And so if you look at this formula here, this is the population standard deviation. Well, if we square this, so if we take that sigma and we square it, what we do to one side, we've got to do the other. So if we square root this, or not square root, but square this whole expression, then the square and the square root are going to cancel out. And we would just be left with what's under the square root in this case. So it's going to be the sum of those square deviations divided by n, like that. So we just took that square root, kind of brought it to the other side, and showed it as an exponent. And so whenever you see sigma squared, what they're usually asking is for the variance. And in this specific case, it's the population variance. Right? So that's the population variance, that's the population standard deviation. And as I've mentioned, the standard deviation is the more popular measure that you're going to be running into. So now let's move on to the sample standard deviation. So we dealt with the population standard deviation, population variance, and the sample standard deviation. In most textbooks, in most classes, instead of sigma, the sample standard deviation is actually represented by an S. Now, not always. You may have to adjust according to whatever textbook you're using, and sometimes profs will just let the sample standard deviation be represented with sigma. Most cases, sigma is population, S is for the sample. But make sure you're adjusting accordingly to your teacher or to your prof. Some profs, some textbooks don't even talk about the population standard deviation. I've seen that. They'll just talk about the sample standard deviation. It's usually the more popular one that's used in courses. But for this video, I'm going to differentiate between both of them. Sigma is for the population, S is for the sample. And the sample standard deviation, very similar formula to the population standard deviation. So we're still going to be taking the sum of those square deviations, but now in the sample, the observations in the sample, not all the observations in the population. And remember, the number of observations in the sample, as I mentioned before, is not capital N, it's small n. And so what we're going to be doing is we're going to be taking all those observations in the sample and then subtracting the mean. And here's another difference that comes up. The mean for a sample is usually represented with this x bar here. And then we're going to square those deviations. Okay, so this mu here was the mean for the population. And then this x bar here is the mean for the sample. Now again, some profs, some textbooks, they might use mu as the mean for the sample, or they might use x bar as the mean for the population. These could all be interchanged. I'm just showing you what comes up in most classes and most textbooks, but make sure that you're adjusting accordingly to your class. So in this video, x bar is the mean of the sample. So it's basically the sum of those observations of those small n observations divided by small n, which is the number of observations in the sample, right? That is the mean for the sample. So we're taking all the observations like we did with the population. It's the exact same thing. We're taking all those observations in the sample and we are subtracting that sample mean. So sorry, this would be x1, x2, x3, all the way to x small n. Okay, we're going to see how much variation there is for these observations from that mean. And then as we did here, what we're going to do is we're going to square all of those deviations. The reason why we square the deviations, by the way, I didn't mention this in the population standard deviation, is because a lot of times these are going to be negative. So for example, let's say that the average is 10 and one of the observations is 8. Well, when you subtract these, you're going to end up getting -2, right? But let's say that another observation was 12 and then you got 10, and then this would end up being +2. Well, if you don't square them and you just add these up, notice that they're going to net out to 0, right? But there is variation in the data. It's varying between 8 and 12, right? And so what squaring these deviations allows you to do is it allows you to change everything to a positive number. So this would end up being +4, this would end up being +4. And so we work with those square deviations, take the average of them, and then we square root it to kind of neutralize this effect of squaring all the deviations, if you will. Right? So that's why we're squaring them, just to change everything to a positive. Because if we didn't, then stuff would even net out to 0, and we would think there's no variability. But as I just showed you here, there is variability between 8 and 12. Right? So that's why we're squaring them. So we're going to square the deviations, get everything to be positive. We're going to sum them up. Right? Remember, this is all for the sample. And here's where a big difference comes in and confuses a lot of students. And I'm going to explain why this is going to happen. You would think that we're going to sum all these up and then we're going to average them like we did here. So we would divide by n, right? Well, unfortunately, it's not just n. We have to divide by n-1. And I'm going to explain why in a sec, why this happens, why we're dividing by n-1. But just remember, for a sample standard deviation, you're not dividing by small n, you're dividing by n-1. And that's the formula right there for the sample standard deviation. And if you wanted the sample variance, well, same thing as here, you would just square both sides. So the sample variance would be the sum of those square deviations divided by n-1. So this here is the sample variance, and this here is the sample standard deviation. So just be careful with what they're asking you in certain questions. Some questions they may ask you for the variance, some questions they may ask you for the standard deviation. And you have to know how to go from one to the next. It's super simple. As I mentioned, standard deviation is always just the square root of the variance. But yeah, just be careful with the questions that you're getting. But again, as I mentioned, more often than not, you're going to, they're going to be asking for a standard deviation instead of a variance. So now let's talk about why do we have to divide by n-1 here when we're calculating the sample standard deviation and the sample variance. Now I'm going to give a brief explanation of why it happens. And what this is called here, dividing by this n-1, it's called Bessel's correction in stats. So if you want a real technical explanation about this, you could just Google this. There's a pretty comprehensive Wikipedia article on it. I'm going to give you just sort of a general explanation of how I think about why this happens. And I feel like this general explanation is just going to be enough. I don't think they're going to ask you too much. They may ask you, why do you divide by n-1? You could just give them this explanation that I'm about to give you. You should get full marks, but depending on your prof, they may want real technical details. So if they do, you can read that article on Wikipedia. Okay, so why we're dividing by n-1? Usually what happens is, let's say that we got this population here. Usually in a population, most of the data is going to be grouped in a certain area. This is for a population. But there's also going to be some data points that are outside of that group, right? But most of the data, when you're observing most data, it's usually going to be grouped, especially if you're taking a large population, looking at a large population. the pattern is it's usually going to be grouped within a certain area. And so when you take a sample of the population, usually most of the data points that you're going to have in your sample are going to be from this group here. You may get some data points from these groups outside here, but because most of the data is going to be from here, your sample is going to contain mostly this data. So the way you could think about it is you're taking a sample from here, but really the population extends all the way out there. And so what happens is when you find the variability of a sample, it's going to be that, but in reality, the population variability, the population standard deviation or the range is usually going to be like that. It's going to be way more, there's going to be way more variability in a population than in a sample. And so that is why, that's the beginning of why. I'm going to explain technically why it's n-1. But to start off, basically, there's always more variability in a population versus its sample. There's usually more variability in a population versus its sample. So the sample variability, sometimes you'll see it described, has a downward bias. And so to counteract this downward bias, what we have to do, what statistics makes you do, is instead of dividing by n here, small n, you divide by n-1 to make this number bigger, to counteract that downward bias. Because if you think about it, let's say we take 10 and we divide it by 5. That would give us 2, right? But what if we take 10 and divide it by 5 minus 1? Well, we're going to be taking 10 and dividing it by 4 now, which would give us 2.5. So notice how that final number, because we're dividing by that value minus 1, by a smaller denominator, it makes that value go up. So it's going to make that sample standard deviation go up. So basically, dividing by n-1 deals with that bias, or maybe another better word is counteracts that downward bias. Okay, so basically stats doesn't allow you to take a sample and say, oh, well, we're only dealing with this much variability. They say, no, 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 you're not dealing, they won't allow you to take this variability and then generalize it for the population. They're saying, no, 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 you took a sample. We know that there's a downward bias and variability for a sample. And so we're not going to allow you to use this variability here to generalize the whole population. We're going to make you up this number, up this sample standard deviation. And so we're going to make you divide by a lower denominator to bring that number up. And actually, dividing by this n-1 doesn't always take this variability and bring it up to this variability. We're actually going to see that in the example that I'm going to do. So a lot of times, even with that correction, the variability, the sample variability might just be over here. Okay, it's still not going to accurately or fully accurately represent that population variability, but nevertheless, it represents it more closely, right? Versus this variability, it's going to be this here. But again, a lot of times it's not even, this won't even be representative of that whole population variability. Right? So anyway, hopefully you got that explanation. That's the reason why you're dividing by n-1, is because that sample variability has a downward bias when you compare it to its population variability. And so we divide by that n-1 to make the denominator lower, to bring up this number to more closely represent the actual variability of the population.